Today we're going to be talking about relative motion. Motion depends on your frame of reference. Walk forward on a moving bus. How fast are you moving? Well, in reference to what? Other passengers or the road? Let's say you're in a bus and it's moving 40 miles per hour north. And you get up and you walk forward at 2 miles per hour. How fast are you moving? Well, two different answers happen, depending on who you ask. Somebody outside the bus, it looks like you're going 2 plus 40 or 42 miles per hour north. Other people on the bus would say you're actually only moving at 2 miles per hour north. There are two very different answers depending on what your frame of reference is. Okay, let's look at some problems with this. Alright, you got a ground-based observer. You have a passenger moving relative to this train, and that's how that's read, passenger relative to train at 2 meters per second. You got the train relative to the ground at 9 meters per second. The question is what is the speed in reference to the ground, relative to the ground, in other words? Well, what you're looking for is the passenger relative to the ground. But you don't have that. You have passenger relative to the train, and the train relative to the ground. So what you need to do is set the problem up in this way. You're looking for passenger relative to the ground, but you have passenger relative to the train, and you have train relative to the ground. Basically what you're doing is, if you look at the two outsides, that's what you want. Passenger relative to the ground. Train and train. A way of thinking of this is like when you're doing metric conversions, and sometimes you actually convert from, say, kilometers to meters, and then meters to millimeters. You're kind of using like the meters as a middle ground. Here you're doing the same thing. So whenever you set these up, the two inside terms kind of cancel each other. And so you're left with the two outside terms. So the answer simply is 11 meters per second. You would have your 2 meters per second plus your 9 meters per second, or 11 meters per second. So that one was kind of easy. So let's try one that's a little bit more difficult. The engine of a boat drives it across a river that is 1,800 meters wide. The velocity of the boat relative to the water is 4 meters per second, directed perpendicular to the current. The velocity of the water relative to the shore is 2 meters per second. And here's a picture. So you got the boat going completely perpendicular at 4 meters per second. So that's the speed of the boat relative to the water. And the speed of the water relative to the shore is 2 meters per second, going down. Okay? What is the velocity of the boat relative to the shore? So now we have boat relative to the water, water relative to the shore. So now we need to actually find the boat relative to the shore. Alright, so here we go. Boat relative to the shore would be boat relative to the water plus water relative to the shore. Okay? The two insides cancel out, and you're left with boat relative to the shore. So these are perpendicular to each other. So you're going to have to use Pythagorean's theorem and the inverse tangent. So what is the speed? The speed ends up being 4.5 meters per second at an angle of 63 degrees north of east relative to the shore. Alright, a little follow-up question. How long does it take the boat to cross the river? Well, does the speed of the water have anything to do with going this direction? In other words, does X have anything to do with Y? The answer is no. The time to cross the river has nothing to do with the current. If you're going across at 4 meters per second, it has nothing to do with the current. Now, will you end up further down the riverbank by the time you cross if the river is going faster? Certainly, but it shouldn't affect the time it takes to cross. It will not affect the time it takes to cross as long as you continue across perpendicular. Okay, let's try another problem. Here we get a car A moving to the east. So its velocity of car A is read as A relative to the ground. We have car B moving north. That's the velocity of B relative to the ground. And the question we have is, what is the velocity of car A relative to car B? So in other words, we don't want to know about the ground. We want to know what car A looks like according to car B in reference to car B. All right, so let's put some numbers in. Car A relative to the ground is moving 15 meters per second east. Car B is moving 25 meters per second north. And here's our equation. A to B. A to B with the ground as intermediary. But we don't have ground to B. But we do have B to ground. And they're actually opposite of each other. For example, we can think of the car in reference to the ground as going north. Or we can think of the ground in reference to the car as going south. I hope I said that right. Try it again. We could think of the car as going north as in reference to the ground, or we could think of the ground as going south in reference to the car. Okay, so these two are the same thing. Okay? V of the ground reference to car B is the opposite of car B in reference to the ground. So putting the numbers in, well, let's actually draw a picture of it first. We got the velocity of A in reference to the ground, and we got velocity of B in reference to the ground, but in the opposite direction. Okay, because we're actually measuring in reference to the car, how it sees the ground moving, in other words. And what we're going to try to do is find this resultant. And we've solved the resultant the same way we always do. We're going to use Pythagorean's theorem. Okay, the negative cancels out anyhow because we're only looking for a magnitude. And the angle is 59 degrees. So what does this mean? Okay. All right, imagine we are in car B. What does it look like car A is doing? Regardless of the ground, we're not taking into account the ground whatsoever anymore. If we're in car B, what does it look like the car A is doing? It looks like it's falling behind it, because in reality, car B is going forward, but to car B, it looks like A is falling down at the same time as going to the east. So it looks like it's doing both these at the same time. So according to car B, car A looks like it's moving at 29 meters per second at an angle of 59 degrees south of east.